Hello and welcome to my tutorial on Newton's laws of motion. So we're going to talk about Newton's first law first. And Newton's first law of motion says that a force is needed to change velocity. And the velocity will not change unless the resultant force acts on an object. A body will stay still or move in a straight line at a constant speed, unless there is a resultant force acting on it. If the forces aren't balanced, the overall resultant force will make the object accelerate. This could be a change in direction, or speed, or both. So, what it's saying is, I need a greater resultant force here in order to get it to accelerate that way, but equally I can make it go backwards by increasing the resultant force this way. And an example of a Newton's first law pair is when you have a book on a table, gravity's pushing it down, and the table is pushing upwards on the book. This is what's known as a Newton's first law pair, where they're two separate interactions, but the two forces are allowing that book to stay on the table. So now we'll look at Newton's second law. So the resultant force is the mass in kilograms times the acceleration in ms minus 2, or meters per second squared. Sorry, meters per second, and it's represented as F equals ma, or the resultant force equals the mass times the acceleration. The resultant force is the vector sum of all the forces. The force is always measured in newtons, and the mass is always measured in kilograms. The acceleration is always in the same direction as the resultant force is measured in meters per second per second. And if the more force you have acted on a certain mass, the more acceleration you'll get, and the more mass you have, the less acceleration you get. So I'm now going. So this jumble down here is actually going to prove that all objects are falling at the same rate if you ignore air resistance. So we take mass m1 and acceleration a1 and resultant force f1. We can put it into a mathematical equation. F1 equals m1 times a1, which is also equal to w weight 1, which is also equal to m1 times the value of g, which is 9.81 newtons per kilogram. And if you do a little bit of tidying up, you can cancel out to m1 times a1 equals m1 times g, and you just cancel out the mass. Acceleration is proportional to 9.81 newtons per kilogram. Well, when it's a falling body, it's accelerating at that exact same rate, 9.81 meters per second per second. Now the same can be applied with a different mass and a different acceleration, but they all still cancel to 9.81. So the acceleration is independent of the mass, and it doesn't make any difference whether the weight is heavy or light. So by showing you two identical examples, I'm showing that 9.81 is constant. There are some fluctuations around the Earth's surface, but they're so minor that as a student, you just have to remember that it is 9.81 newtons per kilogram. So we'll move on to Newton's third law, and this is where you can easily get confused with Newton's first law. So, if object A exerts a force on object B, then object B exerts an equal but opposite force on object A, and that is what Newton pretty much said. And if you also push against the wall pushes back with the same force. Newton's third law pairs are consisted of the same type of force. Now, these two forces, we'll go back to the book and the table. The book has a gravitational force, and the table pushing upwards on the book is a different force. It's not the same as the gravitational force. They also result in zero acceleration, so it actually shows Newton's first law. If something has zero acceleration, and it expresses Newton's first law, but when it expresses a resultant force and it has acceleration, but with Newton's first law, it has to exert an equal and opposite force. So if I have a stick man and he does lean against the wall, apologies for my rubbish stick man, then the wall will have this force equal and opposite to the person. So it's got to be exactly the same, for if it were bigger, then the man would break the wall like that. Well, not really like that. Walls don't bend, but he'd knock over the wall if he put a resultant force that the wall greater than the force that the wall could push back equally and opposite. There's a couple more examples, so we'll have a look at those. If you pull in a cart, so we'll get our Minecraft cart. And you get a rope. I don't know if you could do this in Minecraft. And you get your man. I think his name is Steve. I can't remember. I've never played it. And he pulls it this way. Then the cart is also going to resist with the same amount of force. But this is ignoring the fact that the rope stretches. If the rope is stretching, then the force will change, but we'll talk more about that with Hooke's law. So now we'll move on to some questions talking about force diagrams. So what a force diagram basically is when you have a body of mass, you can represent their forces like this weight having a gravitational force, and if it's on a table, it could also have a reaction force. Don't forget it's equally. It's just I haven't drawn it so it has enough space. The reaction force is always equal to the gravitational force. So it can be also written as R equals mg. Reaction force of the table pushing the mass up to the weight mg. So that's what question 1 asks you to do. Draw a diagram to show the forces acting on the parachute, accelerating downwards and having reached terminal velocity. A boat is moving across the river. The engines provide a force of 500 newtons of right angle to the flow of the river, and the boat experiences a drag of 100 newtons in the opposite direction. The force on the boat due to the flow of the river is 300 newtons. The mass of the boat is 250 kilograms. And what you need to do, I forgot to type it up, whoops, So I'll just type it up here now. So you need to calculate the magnitude of the resultant force acting on the boat, and calculating the magnitude of the acceleration on the boat. So I'll just type it in now. So, question 3 asks you to explain, using Newton's second law, 3 different situations, 2 cars having different maximum accelerations. How Michael can always beat his younger brother Tom in a sprint, however short the distance. Give 2 possible reasons. And Michael and Tom seem to be taking the same amount of time to drop from the diving board to the water, and you need to explain why. Okay, so I'll give you a 5-second pause now. Okay, hopefully you should have paused the video and had a go at the questions, so now we'll look at the answers. So for 1A, you could have drawn weight here, or they tend to favour this ROM, but the question wasn't exactly clear as to whether you need to represent air resistance along with weight, but that one probably has more of a preference over that particular answer. Having reached terminal velocity, you will get air resistance, which is also equal to the weight. So the arrows will be should be the same length when you draw it with ruler and pencil in your exam. 2 part A. The force perpendicular to the river flow is 500 minus 100, which is equal to 400 newtons, and the force parallel to the river flow is 300 newtons. So knowing that, I will now draw a triangle. Oops. So shorter side is 300, 400, and there. So the hypotenuse is 500 newtons once you do your Pythagoras of taking the squares of these 2 sides and then square rooting it. Just put it neatly in that square root sign there, which should equal 500 newtons. Now rearranging Newton's second law, F equals ma, simply by divided by the m, you can get F over m equals a. So rearranging that formula, you will get 2 ms minus 2, which is pretty convenient. So the resultant force is acting on it in part A. Michael can exert a greater force than Tom, and Michael is also lighter than Tom. Weight equals mg, and if F equals ma, ma equals mg, or a equals g, and the acceleration is independent of the mass is another reason. So that's it for this tutorial. Thank you for watching. Next tutorial we'll talk about mechanics in the real world and what you need to know about that.